felt your So you guys have all the sections are going today, right? This week. Yeah. Okay. All right. Okay. Are we good in the back? Okay. Yeah. Side. Here. Side. Good. Okay. Thank you. Okay. Well, welcome back. Hopefully, you all had a good spring break. A couple things. Here's the grade distribution. Actually, it's pretty similar to the last exam. Looks more A's and A pluses, but pretty similar. And I'm sure your GSIs are going to go over the tougher questions in the exam just to give you a feel for what to think about as you start preparing for the final, which is only like 7 classes away. Anyway, we're going to post this one. This is from Colin. Yeah, okay, all right. So a couple things over the break. As some of you probably even participated in it, this March to Save Our Lives. I'm not going to make any political statements about it, other than to say that I was arrested in anti-war demonstrations when I was your age in Chicago. So I'll leave it at that. But a couple things came out this past week, which I have to address in a class like this, because you're the future leaders of this country. And one of them had to do with one of our ex-senators, Rick Santorum, who I refer to from here forward as Lunkhead, Sanctimonious Santorum. Hopefully that gets transmitted to you somewhere, Lunkhead. He came out and said that what you need to learn to do, if someone comes into this room with an AR-15, is learn how to do CPR. I got bad news for Lunkhead. CPR doesn't work if you bled out, right? I mean, it's just ridiculous. So that whole logic is just disgusting. The second piece of news is from another political pundit, an ex-congressman who's equally as disgusting. The new approach by the gun lobby, which is really just interested, in my opinion, in making money, is that if you say you want to ban assault weapons, these are military-grade weapons. If you say you want to ban assault weapons, all guns are assault weapons. Therefore, you're saying we want to ban all guns. That says these kids are out to get rid of the Second Amendment. This is, again, absolute garbage and intentional garbage. In fact, this little lunkhead was smiling as he made this comment. I'd love to get involved in a debate with these bastions of liberty. Let me show you reality. Here's reality. Here's a low-velocity bullet, a .22, or let's say 38 caliber weapon. You unfortunately get shot. That's where the bullet hit. Yes, the bone is fractured. Yes, there's some bullet fragments and some bone fragments, but a surgeon, an orthopedic surgeon, can put that back together. Okay? That's a low-velocity bullet. Let me show you what happens when the same bones in a different person, the same tibia and fibula, get hit by one bullet from an AR-15. Okay? You don't need to be a rocket scientist to see what the difference is. The bullet has completely destroyed the bones. It tumbled and rolled, took out the fibula and the tibia. This thing will never be normal. This person will be maimed for the rest of their life. There's no way to fix this. And that's the difference between high-velocity, automatic weapons of war. So, lunkhead sanctimonious santorum, if you see this ever on the web, feel free to call me and I'll try to educate your ignorant mind. Was that political? No? Yes. Sorry. I know some of you may think differently, and guess what? I don't care. Okay. So now on a more positive topic, many of you earlier in the course told me that you, remember when we had the Wiles here, where they visited the class, and about a third of the class said they were working in labs, which I think is absolutely fantastic. I'd just like to introduce you to something more positive than AR-15s, and that's a journal called Frontiers for Young Minds. And I'm introducing this to you because any of you who work in labs with postdocs or grad students or PIs, you could actually participate in this, I think, really exciting, journal. The journal basically flips the scientific process. It's very simple. You're working in a lab with a postdoc. You have a new paper that went out, or you have an idea about all the field in olfaction. You can submit a paper to this journal, 3 to 4 pages, 3 to 4 references, 3 to 4 figures, and it's reviewed by kids between 8 and 14. The kids act as reviewers, and they actually are paired with a mentor who could be a postdoc, it could be a grad student, could be another scientist, it could be an individual kid, it could be a classroom of kids, it could be your 2 nephews in Philly that you'll talk to them on Google Hangout, whatever. So scientists write an article. For kids 8 to 14, it could be a new discovery, a brand new paper, let's say on corn alcohol, or it could be a core concept. What's color vision about? So there's 2 kinds of articles that are accepted. The article goes to kids, right? Think about that. The article is reviewed by a science mentor and a young mind. The researchers have experience in peer review. They try to really teach the kid what it means to understand what's a hypothesis, what's an experimental design, how do you collect data, how do you analyze data, how do you write the data up for publications, and then how do you deal with the scientific review process that gives you feedback as to whether your paper needs to be improved in this or that way. So it's really a pretty exciting venue. There's 6 areas now. Neuroscience, because it started at Berkeley, and that's what I do. But we now have health, biodiversity, Earth and its resources, space and astronomy, and mathematics. There's going to be a 7th area based on the input from the kids who participated. And actually, what do you think the 7th area is that the kids want the most? Anybody have an idea? Guess? Robotics. So they're all excited about robotics. So we got to get a chief editor for robotics. Each article, it's open access. You can go to it right now, download any article you want. We're in our 4th year. We've had 537,000 journal hits already and growing exponentially. Each article gets a cartoon. So you could probably look at this cartoon and say, that must be space and astronomy. That's actually an article on, is there life on other planets? Here's one on carbon in Earth and its resources section. Here's one on health. What are stem cells? How do they work? And here's one on concussion, which is in the neuroscience, but could be in the health section. So very easy, accessible. The kids are brutal in terms of the reviews. You don't get these from adult reviewers. It would be helpful if they told us how they took the measurements of brains without actually having to remove the brain. That's a 9-year-old reviewer. The writers of the article did not make it clear why such an expensive and involved research project was done to begin with. It seemed like a fruitless task. That's a big ouch, right? The point is not clearly expressed. I didn't understand the main scientific question because there were so many details at the beginning. Maybe state what the main question is earlier in the manuscript. This applies to everything in terms of writing, not just scientific. Anything you're going to write in life, you got to capture the people's interest and tell them why it's important. And then finally, my favorite review from 4 years of seeing reviews from kids. This is the one you definitely don't want to get. And you would never see this in an adult journal, but you think it many times. This seems important, but the way it is written is so boring I can't even get to the end. Could the authors maybe sound excited about what they are doing? So, yeah. Anyway, take a look at the website if you're interested in publications, and there's actually an undergrad working in Daniela Kaufer's lab, and they wrote a paper together. It's being presented at the Neurobiology of Learning Symposium down in Irvine. So, take a look, see if you're interested. All right, back to the actual course material, and we're now going to talk about the frontal lobe, probably the most sophisticated and advanced part of human evolution. This is what placed you in this room. You're able to handle lots of information, sort it, select it, stick it into memory slots, integrate it with reward signals, make decisions. All these kind of complex things that we do fluidly and effortlessly are really dependent on our frontal cortex. It's been a mystery for many years on how it does this. So these are giants of neuroscience. Hans-Georg Teuber, he referred to the frontal lobe as a riddle. A.R. Luria, my favorite neuropsychologist, called it the youngest and most complex portion of the cortex, 1969. Wally Norda, another unbelievable neuroanatomist for MIT, referred to the frontal lobe as mystifying. People were having trouble getting a handle on what it precisely did. Unlike if I take out motor cortex and you're paralyzed, right? Or I take out visual cortex and you got a hemianopsia. The frontal lobe was not so easily tractable in defining what its important functions were. Great for final exam questions. Don't forget that. I don't know why that's in there. Okay. So the riddle of frontal lobe function goes back to 1876 with David Ferrier, a brilliant British neuropsychologist. We talked about him earlier in the course briefly. He actually defined what visual cortex was and auditory cortex. He took out the frontal lobe bilaterally of what he said were his three smartest monkeys. Okay? And if you notice, the cut he made took out both lateral frontal, orbital frontal, and mesial frontal. So it's a complicated ablation, but a lot of tissue was gone. What did he observe? And this guy's a really brilliant observer. And I'll show you what he had in a minute. In parallel with him, Alexander Romanovich Luria, based on observations of humans with frontal lobe damage either from bullet wounds in the war or stroke or brain tumor, a whole range of miseries that we've discussed. He said the frontal lobes are essential for organizing intellectual activity as a whole, including the programming of the intellectual act, deciding what you're going to do, and then monitoring your behavior to see, did I get it right? Do I want to adjust? Do I want to do something a little bit different the next time I try to do this, that, or the other thing? This is a brilliant book by him, The Working Brain, which actually is the book that when I read it, I decided to go into human physiology research. So here's Luria and abstract thinking. Abstract thinking involves organizing thoughts and constructing conceptual schema of ideas. And the frontal lobes are needed for planning thoughts and reasoning and monitoring and controlling thoughts. So this is a picture that you show to you, and you right away say, my God, a kid fell through the ice. The people are coming to save the kid. You construct a whole story. You show that same picture to someone with frontal lobe damage, and they say, oh, there's somebody over here, and there's some people pointing here, and here's someone kind of laying on the ice, and here's someone, they may have fallen through the ice, but they don't put together a story. They see the elements, but they don't put it together and weave it into a coherent, intelligent story. And this is how we test these patients at the bedside all the time. I have little things that I ask them, tell me a story. Now, I want to go back here because I dropped out a slide here, and I just want to mention here, when Ferrier did this, he said that these monkeys became disinterested and lost their ability to pay attention. They just were not interested in their surroundings. And as you're going to see, that same thing happens with humans with lateral frontal lobe damage. Now, you can get lots of different diseases can affect your frontal lobe. And first, we're going to talk about lateral frontal. And then next Wednesday, we'll be moving into orbital frontal. And we're going to put the lateral frontal in a bucket that includes cold cognition, executive control of thinking and planning, things that are emotional, even to some degree asocial. Whereas when we talk about orbital frontal damage, we're going to be talking about problems in social interaction, integrating emotional signals with decision, etc. You can see here from what we've done in this course already, there's a stroke in the frontal lobe, a hemorrhagic stroke. Here's a bad infiltrating glioma. Here's a frontal temporal dementia that we've discussed with this knife-like atrophy of the frontal lobe. And here you can see a big cortical malformation, a cortical dysplasia, one of the more frequent causes of uncontrolled epilepsies in kids that we have to eventually do surgery to take that out and get them under control. When we go into the orbital frontal lobe, we'll be talking about trauma. We'll be talking about orbital frontal meningiomas, and yes, even frontal temporal dementia can not only get lateral frontal, but often starts with orbital frontal and anterior temporal amygdala, which we'll really talk about in terms of neurobiology of emotion. So again, the subdivisions: lateral, cognition; orbital, social emotional; medial, cingulate regions, interplay, like sending information back and forth between the two areas. Oh, I had some emotional feeling. Let's see if that influences how the frontal lobe's going to make a decision. So these are not operating as individual islands. These are all heavily connected and rapidly moving information around so that everybody in this room can make the appropriate kind of decisions you want to have a really good life. Now, we talked about this a little bit before, earlier in the course. You have your primary cortical areas like motor and somatosensory and visual and auditory, and then you have areas near these areas. So these premotor areas are more involved in motor control. And these areas here are more involved in extracting visual information, let's say color and shape and form, etc. And we'll get into those a little bit later in the course. But the area we're talking about now are the pink or the salmon areas. These are your areas that are called association cortex, tertiary areas. They don't care if it's auditory, visual, somatosensory, internal thought. It doesn't matter. They are information managing system, right? They're trying to take information that's come in from the periphery and turn it into meaningful information for decisions. And you can see this massive evolution, or the massive size, I should say, of the prefrontal cortex, one of the last areas to develop. So lateral prefrontal cortex, executive control, cognition; orbital, social and emotional behavior; medial, interplay, and monitoring of behavior. As a first pass, each one of these areas has now exploded from the 70s and 80s, when we didn't know much, into massive fields of research. And I'm trying to give you a feel on how to think about this. Now, this lateral frontal cortex and parietal association cortex, one of their key features is they have massive bidirectional connections. So, for instance, what's a unidirectional connection? Your motor cortex fires and it goes down your spinal cord and your hand moves. That's unidirectional. The frontal lobe is constantly putting information out and getting information in. It's a bidirectional highway. And it's the biggest bidirectional highway in the human brain. And you can just see this here in some monkey data showing that pretty much every area has connections to the lateral frontal cortex. And it even gets more complicated. There's massive connections between sub-areas of the frontal lobe moving information around. And you say, why do we do this? Well, I think it's really simple. We're fast. We make decisions in a third of a second. We got to move information around quickly. We've got to have a lot of information moving around really rapidly to come up with proper decisions. And luckily, we have large connecting fibers in the brain, which have 50 meter per second conduction velocity, so I can get a frontal signal to the back of your brain in 10, 15 milliseconds. So this allows you to do all these things that you do so effortlessly, this massive control system, if you want to use an engineering province. Now, the other interesting thing about the frontal lobe and the rest of the brain is your primary areas, which would be vision, motor, audition, somatosensory. The bigger the circle, the earlier that area myelinates. Myelination means the axons that are coming out of an area are getting their final coating and they're set to function. They're set to communicate with the rest of the brain. If you look at the size of the dots, the farther you get away from these primary areas, the smaller the dots get. And that simply means that these are the last areas to myelinate. So your complete control of your frontal lobe is not done for a long time, at least into your 20s. And actually, you change over life and you learn new things. But the brunt is done by maybe you're 20. And so the purple is the last area to myelinate. And this is from 1919 on postmortem studies. This is basically on more modern fMRI studies. And you see the same deal. Last to myelinate, last to myelinate. Again, major changes occur in the myelination in two key areas. We don't know a lot about kids below age 4. And the reason for that is it's hard to get them to keep still in a magnet and get any information. It's as simple as that. And you're not going to sedate a kid just for a research study. But we do know, and any of you who have SIBs, there's huge changes between the ages of 4 and 6 when lots of language and decision and kind of theory of mind and understanding other people, all those things begin to come online. Very critical time in child development. And then there's another massive area, massive change in the development of the frontal lobe that we see between the ages of 11 and 14, the teen years, which you've all just recently been through. And in part, that's contributes in part to some of the. You don't have a complete. You're smart, but you haven't have a completely tuned regulatory system. Your frontal lobe, both your lateral and your orbital, is not done getting to at least a level where it's kind of who you are in terms of the kind of decisions and the way that you deal with the world. So these are very important developmental cycles. In fact, there's a T-shirt that is out there that says, for teenagers, that says, "It's not me, my frontal lobes are not developed," which we should get those for the lab, right? No? Yes? Huh? No, I didn't mean for you. I meant to give to people you know, Colin, like kids you know down in New Orleans. I'm sure they've got problems. No? They're in New Orleans. We have a little Pelicans Warriors thing. You guys don't care about sports. So let's move on here. And that's why people don't like, you have higher rates of insurance for teenagers. It's not because teenagers don't have the reflexes to really drive better than someone who's probably me in terms of their, they've been playing games, they're super good. Their frontal lobe is actually not quite developed, and they make bad decisions. They can get influenced by other people in the car. That's why a lot of the driving things now, as you know, you can't drive without an adult, you can't drive at night, yada, 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 trying to decrease the amount of car-related injuries and mortalities in kids. Now, the prior dogma on the size of the frontal lobe is a really interesting story. This held to about 2000. Up until about 2000, if you read any book, it said that the human cortical mantle is about 35% of your brain, okay, of your cortex. That's a lot. And then there was a precipitous drop-off to a high-level chimp where it was down to 11 to 12%. Then, if you go down the species and you go to a dog is about 7%, which is pretty good. Dogs can still kind of have a relationship with you. Now, are there any cat lovers in this room? Cat lovers? Yeah, I got sad news for you. You really don't have a relationship with your cat because your cat really only has about 2% of its frontal lobe is actually 2% of its cortex is actually frontal cortex. So they're basically a reflex animal. Just the way it is. Now, this dogma got addressed to some degree in 2002 by Semin Deferi, an anthropologist at UC San Diego, who actually laid it out a little bit differently. She said, 35%, and chimps maybe 28%, and gibbons and so on, macaque monkeys, a favorite species for brain research, about 28%. So she bumped up how much cortex was in the how much frontal cortex there were in species below humans. Now, I think I don't think she moved the needle from almost, way down in other species to close to humans, but the true stories actually just come out with even more extensive imaging. This was based on some early imaging work. This is from work from David Van Essen's lab, and I think this is closer to the truth. This just is coming out now. In the humans, it is about 35% of your cortex is frontal cortex. Humans are about 24% greater amount of frontal cortex than a chimp. So not so far off from semendeferi, but quite a bit more than macaques, where she said 28% roughly. It's actually probably closer to maybe 15 or 18%. So humans are 85% more frontal cortex in a macaque, which is a very popular model for studying cognition, than in the human frontal cortex. So these are the true numbers, I think, now, because this is a really huge, big study. But semendeferi gets credit for, going after a dogma that was not correct. Now, what else besides the size matters? I told you bidirectional. So if it's bidirectional, it must mean you got to have increased wiring, right? If you're going to, it's as simple as that. And so here's the data. It's really simple. If I take a chimp, which is the closest to humans, and I do a cut through their frontal lobe, and I look at the amount of white matter, and I do the same cut through humans, and I look at the amount of white matter relative to the cortex, right? The cortex in blue and white matter, I think it's pretty easy just from looking at this. There is a massive increase in the amount of white matter in your frontal lobes, right? It's actually, per the Van Essen study, there's 75% more white matter in your frontal lobe than in the next highest species. So that is really, if you will, the engine that's helping you do all the things that you do to be as successful as you are. Now, so that's a little bit of the development of the anatomy of the story. What about cognition? Let's talk about cognition a little bit. And let's do some of the characteristics of people who have frontal lobe damage. And it could be from any misery. We've talked about all of them, not all, most of them in this class. Stroke, tumor, trauma, degenerative, chronic traumatic encephalopathy. Pick your poison. Generally, relatively normal intelligence on IQ tests. So the mean of the frontal patients is probably close to the mean of the population, which is 100. Now, it's a little bit of a false number, because if you actually do IQ tests that are not rote and you check creativity and more advanced problem solving, the frontal patients are going to have problems. But in general, they walk and talk and look like most normal people. They have working memory impairments. They don't have hippocampal problems. Their hippocampus is intact. But remember, they can't keep things in their mind's eye for a short period of time. We talked about that in the exam. Remember, have the patient repeat baseball tree and window, and then check in 10 seconds, and they still said baseball tree and window. That means their working memory is intact. They could keep it online. This is impaired in patients with lateral frontal damage. There are impairments in executive control we'll get into. We've already gone over in the clinical part of the class all the classic frontal release signs, these baby nipple signs, a snout reflex, a grasp reflex, etc. These are all the things you see clinically that tell you, yeah, the whole thing fits together, right? The patient has these symptoms, these signs, and then you go to imaging and it should confirm exactly what you're thinking about. Many cognitive processes, in fact, you can almost say all high-level cognitive processes are dependent on your lateral frontal cortex. And these are just some of them. Focus and sustained attention, word fluency, flexibility of thought, generation of solutions to novel problems, planning and regulating and adaptive and goal-directed behavior, you name it, right? So right now, and time travel. So right now, all of you could go back, I'm sure, go back in time and think of what you were doing last Wednesday during spring break. Depending on what you were doing, the memory might be a little impaired. But you should be able to bring it up. That's time travel. You went back in time. You can also decide what you're going to do right now, what you're going to be doing in the summer. You probably all have plans. So you're going forward in time, you're going backwards in time. This is a very unique human capacity, and it is dependent on your lateral frontal cortex. For lateral frontal disease, the patient progressively loses the ability to extract themselves from the current situation and time travel. What did I do last week? What did I do this morning? What am I going to do tonight? Etc. So here's a patient that I saw many years ago. He was a lawyer, nice guy. He graduated from either George Washington or Georgetown. It's been so long I don't remember. I think this is a movie from '82. And during his final exam week, in his senior year, he was president of his class, by the way. Had a girlfriend, was a sailor, pretty, guy with a nice, complete lifestyle. He had a seizure. And they thought, well, he's staying up at night and, et cetera, it's sleep deprivation, and he should be fine. They put him on seizure meds, though. He had a CT scan at the NIH, which was negative. They didn't have MRI scanning there yet. So he had a negative CT scan, but the bottom line is a CT scan is negative in 5% at least of brain tumor glioma. So they sent him on his way, and this very nice guy never practiced. Right? He ended up in Florida being a tennis instructor. And after that, he ended up in the Bay Area back with his brother, younger brother, who was a successful lawyer now in Marin, even though he was years behind this gentleman. When he presented to the neurology clinic at Highland Hospital, which is just down the road in Oakland, the resident, like a good med student resident, took a history, said, sir, why are you here? You want to know why the person thinks they're there? And his response was, I've lost my ego. That's what he told the resident. And then a resident presented him to me. I took a look at him. He had a snot reflex. We sent him down to get a scan, and he had an infiltrating glioma on one side that had grown through his corpus callosum into the other side. It had already grown through. Remember how these gliomas follow white matter tracks? So based on that, you knew at that time in 1982, his survival was somewhere between 6 and 10 months. Period. End of story, because it's a high-grade glioma. Now, you're going to see him with me interviewing him. It's a lousy film because I'm the cameraman, the examiner, and God knows what else. This is just after I've told him and his family that basically he has a fatal brain tumor, and he's probably going to be dead in a year. And the family's completely upset, and he's kind of indifferent. He's frontal lobish. He's indifferent to the situation. And he actually makes jokes about it. You felt your ego was disappearing. Could you tell me a little bit about that?
Yeah, that's right. It meant very little to me about setting up a law practice and getting rolling, even though I had gone 4 years of college, 3 years of law school.
Did you have girlfriends in college and law school?
I did.
How about now?
I don't have any girlfriends now, and I haven't been looking for any of them.
Yeah. Do you notice your sexual drive or is decreased?
Definitely.
What kind of problems have you been having if you try to do something? You try to get something done. What stands in the way?
Top of the list is memory.
Mm-hmm.
Working. I can't remember things.
You still, to me, seem a little bit casual about it.
It's true what you're saying. Biff is casual and somewhat jovial and good-humored about it all. 4 months ago, we lost my mother. Mm-hmm. And people remark, my sister and my cousin remarked that Biff has not shown any manifestation of grief.
I don't feel grief.
Now, if I've shown that particular clip to a room full of psychiatrists, and they say it's a midlife crisis, it's some psychiatric problem, it's definitely not. He's just completely indifferent. He has what's called, I'm going to butcher this, the people who speak German can fix it, Witzelsucht. He has facetious jocularity. He's inappropriately lighthearted. He's just been told he's going to die. Doesn't care. This is basically what happens with these tumors. That you kind of lose lots of things that are very important to be a human. Now, this was all in one day. We saw him in clinic in the morning, sent him down for a scan. So the scan, he had a tumor, met with his family in the afternoon. I never saw him again. He went the next morning to UCSF for chemotherapy, which, unfortunately, he did die. Now, the other thing you can get very commonly in the frontal lobe are frontal strokes, which we've talked about. There's your middle cerebral artery. There's an acute frontal stroke. There's a chronic stroke with a piece of tissue taken out. And there's a really chronic stroke where the tissue's just, all your brain tissue's gone, and all you see over it is the little pia and arachnoid membrane. That's what a chronic stroke likes. And in our lab, we do lots of research in these patients because the disease is not progressive. It's fixed. So it's a very good model to try to understand brain function. So here's a gentleman, the next guy I'm going to show you, who had a rare situation where he first infarcted one frontal cortex. He had a heart problem. He had a valve problem, and he was throwing emboli from his heart. And first he infarcted his right frontal lobe, and then he infarcted his left frontal lobe. Pretty unusual. He had two large sequential infarctions involving frontal cortex. And if you did that to the hippocampus, you'd be amnestic. If you did it to the visual cortex, you'd be blind, et cetera, et cetera. But in frontal lobe, it's a different story. Sorry. This is the gentleman, and you're going to see, again, this is the very end stage of frontal lobe lateral frontal problems. He's abolic and completely disinterested and hypo-aroused. Okay, don't do... Okay, he has a bilateral grasp reflex. You've seen that before. You all grasp each other.
Okay. Let me just check some things here.
Right here, watch his lips.
I'm going to tap you. It's not going to hurt. I'm just going to give you a little tap. Can you... Okay. I think you can see there's a very prominent...
That's it.
You say 4+ snout reflex.
And you're going to see he's really under-aroused.
No clear rooting reflex. Open your eyes. Open your eyes, sir. Open your eyes. Open your eyes. Try not to blink. Okay, open your jaw.
Now, if you look at the back, you say, why is he so under-aroused? Well, it turns out, as you sit here, your frontal lobe is orchestrating all this activity throughout your brain, getting feedback information, changing the decision pattern. It's sending top-down excitatory input to most of your brains. And these are the glutamate receptors, which is excitatory. And when you lose your frontal lobe, your glutamate that makes the back of your brain kind of revved up and ready to process is suppressed. So actually, if you look at these patients physiologically, and you just look at their evoked responses, if I give you a flash of light and you have a response this big, if I give the same flash of light to someone with lateral frontal damage, it's that big. They're under-aroused, abolic. They look just like Ferrier's monkeys, who were disinterested and didn't want to do anything. Now, working memory we've talked about, and it basically is defined as the process of keeping information in mind, many control processes, maintaining, manipulating, moving this information around. This is a cottage industry with a massive increase in publications in this area. You can trace it back to some monkey work. And this is some work done by Pat Goldman-Rakich, who unfortunately, by the way, was a brilliant professor at Yale, got hit by a car and had an epidural hematoma. Tragic. Very tragic. Anyway, here's the study. The animal looks here, right? Acute comes up here. Then there's a delay with nothing on the screen. The animal maintains fixation, and during the entire delay period, these single cells in the monkey equivalent of your lateral frontal cortex, which is called the sulcus principalis right here, it fires like crazy, and then the response is at a delay, you now have to look in the direction of wherever that cue was. And when you basically, this is the classic delay period, and then look to where that response is. You can see the eyes moving there. So this is how it was studied. And there are, I don't want to get into the sub-details of this, but that was the first major finding. But if you really go back in the literature, you find that Jacobson in 1935 did a study with monkeys where the monkeys had food in one well. Okay, so there's food. Screen goes down for 30 seconds. You take the screen back up, the monkey basically gets the criteria like that. They always remember where their food was. So they can hold information online for 15 seconds, 30 seconds, 60 seconds, probably even longer. But if you lesion their lateral frontal cortex, either by surgically damaging it or depleting it from dopamine or cryogenically cooling it, the monkey's behavior on this simple delay task goes to chance. They can't even for 30 seconds remember where their precious food is. And we find the same types of effect in patients with lateral frontal damage. So there's a nice cross-species homologies in this behavior. So this is working memory. And I don't want to say it's only in the frontal lobe, because as we've studied it more, we know there's also parietal lobe contributions. I don't want to become frontological. I don't want you to go away from thinking just frontal lobe. These are all complex systems, but without the frontal lobe, the whole complex system falls apart. So the clinical characteristics, again, you just saw flat affect, decrease in drive, lack of self-awareness, behavior, emotions, imitation and utilization behavior. I'll show you what that is. It's very interesting. Here's imitation behavior. The experimenter puts his glasses down and starts doing something. The patient mimics him. Or they pick up the glasses and put them on. Or he goes to comb his hair. The patient combs his hair. They smell a flower. The patient starts smelling. They're not being told to do this. They're imitating the behavior. They're stuck in the moment, really, because they're so fixated on the exact moment. Everything that happens in that moment determines their behavior. They have no ability to go offline and say, why is the doctor smelling the flower? Seems like a weird doctor. No, they basically smell the flower. This is basically imitation behavior here. This is the doctor kneeling down to pray. The patient with the frontal lobe damage kneels down next to the doctor. These are very big behavioral effects. These are not subtle little minor reaction time effects. You see this overtly. If you took the frontal patient into the free field of life, let's say you took him to the Berkeley Art Museum, and you see some really cool painting, and it's got some texture to it, and you think, boy, I wonder what that texture's like. You wonder that, but you're not going to touch the painting. Probably not. But the frontal patient might go up to the painting and actually touch the texture, right? They'd be very stimulus controlled, right? The immediate world determines what their behavior is going to be. They cannot go offline, take that information, and make an effective plan and think, oh, gee, that's a really interesting texture. That reminds me of Van Gogh or whatever you might be thinking of. Okay. Separation of action from knowledge, failure of language to control behavior. This is one of the things people put language at the top of the food chain. But it's not. If you remember that patient we just saw, the young lawyer with the glioma, he was speaking pretty well, right? So his language was not impaired, but as being able to function in the world, actually he was completely impaired. And by the way, when he, I'll maybe at another time. Inability to initiate, stop, and modify behavior in response to changing stimuli. Locked in the present. Inability to organize and plan. Inability to inhibit responses. Let me just show you some examples of this. You guys all have probably, do you know what the Wisconsin card sorting task is? This is a very common task used in many laboratories. So you're basically, the patient's just sitting there, and you give them a deck of cards, and all you have to do is sort the cards. You just say sort the cards. And they start sorting, there's 4 possibilities here. So they say, my sorting criteria is I'm going to put this has got 3, it's going here. I'm sorting it by numbers, right? So if the next card came up was a 1 blue triangle, they'd put it, a normal person would put it there. And you switch between trials. What happens as you're doing this task and you've got your criteria, every time a 3 comes up, you put it here, a 1 comes up is here. Now the experimenter simply says switch. Switch means you have to come up with another sorting criteria. So another sorting criteria that you might pick is I'm going to put the red ones here. Or I'm going to put all the squares together, right? So you have multiple options of what you can switch to. The patients with frontal lobe damage don't switch. They get stuck on set. Even though you tell them to switch, they don't switch. They keep doing the same perseverative act over and over again. Perseveration, perseveration, perseveration. Stuck in set. It could be stuck in a thought set. It could be stuck in a verbal output set. It could be stuck in a motor output set. And that would be proper switching. Prefrontal patients can't switch rules. They stay with numbers or sometimes just make a random mistake. They can go completely offline and lose track of what they're supposed to do. So this is the classic Wisconsin card sorting task. Inability to organize and plan, can't move across the time spectrum, perseveration, stuck in the present. This, to me, is one of the most fascinating aspects of frontal lobe ability, which is what I mentioned to you before. What did you do last week? What are you doing in the summer? And so on. So here's a little cartoon of this. Loss of time travel. Here's the present state. We fluidly can go into a past state or into a future state. Frontal patients get stuck in the present. And here's some nice examples from the brilliant A.R. Luria's work. So these are patients. You can see their Russian names. You basically tell the patient to draw a cross. They draw a cross. You say draw a circle. They start to draw a circle. Draw a cross. They draw a cross. Draw a circle, cross, 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 circle, cross. They're now perseverating. They're stuck in a perseverative set. You say, what am I supposed? You say to them, what are you supposed to draw here? They say circle, but they drew a cross. They're stuck in set. Similarly here, you can see they're stuck in this square set. They're stuck in this circle set, etc., and so on. So this is the very classic clinical phenomena of perseveration, which I've noticed some of our more senior officials in Washington tend to perseverate. I'm available for neurological exams. If anybody needs me, be happy to fly back. Okay. Inability to inhibit responses. I would bet a third. Who knows what the Stroop task is? Got to be. Oh, not that many. About 10% of the class. So we'll do it as a group. This is a pretty classic frontal lobe task where you can't inhibit a prepotent response. It's a very simple task. So what we're going to do is, as a class, we're going to read this way down as fast as we can. Okay? Here we go. Ready? Out loud. Blue. Okay, good. Pretty fast, pretty smooth. Now what you're going to do is I'm going to show you the same letters, but they're going to be colored. And all I want you to do, I don't want you to say what the word is. I want you to say what the color is. And let's see how fast we can do that. Here we go. Okay, well, all right. I think we've proved. We see it's what's happening is your prepotent response in this situation. The language overrides the color system. So even though you're being told to respond to the color of the stimulus, you can't inhibit the response. You're getting them right. You're just slow. You have to do extra effort to not say, whatever, not say blue here, for instance, right? So this is the classic Stroop test, and this is really sensitive to frontal lobe problems. The patients really get stuck in, or are even, as a group, slower than you and more chaotic in terms, more distributed in terms of the responses. So Wisconsin card sorting and Stroop task are nice tests. Now, we'll close out with just a couple slides about the lateral frontal lobe. And, you can see psychiatrists basically too early. And, that's interesting. Let's see how far we get. You can see a psychiatrist too early. This is in the old days, and you could end up with a frontal lobotomy. This is one of my patients who actually had a lobotomy in the 50s. A lot of them weren't lobotomies. They put wires down into your frontal lobe, pass current through, and burn all your frontal connections, basically rendering the frontal lobe ineffective. Or this is this procedure here. Or, and this is the same procedure, or you could do the outpatient procedure where they would raise up the eyebrow, put an ice pick up into your frontal lobe, move it a certain degree, let you go home and see how you did over the next 2 to 3 months for whatever your misery was. Usually it was some form of a psychotic illness, but If you were lower socioeconomic, you got this procedure just for anxiety disorders. It has a horrible history to it, the outpatient procedure. Or you could see this thing is interesting. Okay. You could see a psychiatrist too late. And here's somebody, one of my patients, unfortunately, at Highland Hospital, who actually had a bullet go through their head. Right, there's the track, the blood track, and there's the bullet lodged. This is what it would look like fatally. That's a fatal low-velocity bullet, okay? Still bad. That could be a 22 or 38. If that was an AR-15 and it went in here, this whole hemisphere would be completely emasculated because of the velocity, force, and tumbling of the bullet, right? So actually, this is also gives you some idea when you see a patient like this, for those of you going into anything clinical, that come in and there's a bullet wound. If there's a bullet wound here, you always say, well, what's the handedness of the patient? The patient's found down with a gun. You want to know the handedness, because what hand would you commit suicide with if you're right-handed? Would it be your right hand or your left hand? It would be your right hand. So, in fact, people never do this. So if you have someone who comes in to the emergency room who's right-handed, and the bullet entered here, they were shot by somebody else, and it's a fake suicide attempt. Just a little piece of information. Finally, last slide, this whole thing stopped. This lobotomy thing stopped when it became a traveling outpatient circus where procedures were being done all over the country. And finally, they were starting to do kids for behavioral disorders. You can see this is being done unsterile, where he's actually tapping this thing into the person's frontal lobe. And finally, they started showing pictures in the press of these kids who had these bilateral frontal lobotomies. That led to an uproar, and the procedure stopped. And mercifully, better psychiatric meds start to come in the late 60s and early 70s. But I'm not saying these people were ill-intentioned, but you can see how things can go amiss. And you can get outcomes that probably are not what anybody would. You'd look at this in retrospective and say, what happened? What was going on? So, you're educated, you're a consumer, so hopefully you'll be able to spot these things. All right, so thank you. See you Wednesday. Bye. Hello. Hi. Hello. Thank you for completing.